It's a pleasure to have Yuval Ronen today. Yuval is currently a postdoc at Harvard in the group of Philip Kim. Before that, he was a PhD student with Moti Heiblum at the Weizmann Institute, where he also worked on fractional quantum Hall effect. Did some amazing work, and today we're going to hear about interferometry in van der Waals heterostructures. Okay, so Yuval, the floor is yours.
Okay, thanks. Okay, so I'll talk about quantum Hall interferometry in van der Waals heterostructure. And if you have any question, just jump in and ask. Sometimes with this Zoom, I cannot hear when you ask a question. So be persistent and I'll hear it. Okay, so on the right side you can see a kind of an illustration of the van der Waals layer that we are using, and I'll talk about it as we continue. And on the left, you can see one of the devices that we measured. So it's a colored SEM image of the device, and you can also see the edge structure of the quantum Hall effect, and it basically encapsulates the interference in the quantum Hall effect that I'm going to talk about. Okay, so before we dive in, I just wanted to mention two people that really we did together this work. So Tom is a graduate student in Kim's group, and Daniel is an undergrad. And both of us, the three of us, basically worked for the last 2.5 years on this project and developed this quantum Hall interferometry in the lab. And it's really been a good and educational experience, I think, for the three of us. Okay, so before I talk about interference in the quantum Hall effect, I just wanted to mention two other works that I did in the postdoc, and we are also continuing these approaches. And I'm not going to talk about it, but just if somebody is interested, I'll be more than happy to discuss it privately. So one of them is inducing superconductivity in the fractional quantum Hall effect. So the idea here was basically to merge two many-body effects, superconductivity and fractional quantum Hall effect, in a single device. And this is actually, both of these effects have been here for 40 years, and nobody was able to merge these two effects. And in van der Waals, it's actually possible. And the idea, so first of all, you want to merge these two effects, but also there are new kind of quasi-particles, non-abelian quasi-particles that I'm going to describe what they are, parafermion, which emerge in these kind of structures. Another project that we were working on is Cooper quartet Andreev bound state interference. So here actually the device is more simpler. So it's basically, these are 4 superconducting contacts on top of graphene, and it creates a multi-terminal Josephson junction. And inside this multi-terminal Josephson junction, there are resonative state. There are these Andreev bound state, resonative state that lives inside this junction. And the main idea of this experiment was, so you can think about the Bloch band structure in crystal, which is basically a band structure in the phase space of Kx, Ky, Kz. So here there is a band structure of Andreev bound state in the phase space of phi 1, phi 2, phi 3, okay? And the idea here is to realize a topological band structure in this Andreev bound state in these kind of structures. Okay, so this is the kind of direction that we were aiming here. But today I'll talk about interference in the quantum Hall effect. Okay, so let's dive in. And the first thing, right, when you talk about interference, right, the first thing that comes in mind is a wave. And in quantum mechanics, right, the first thing that comes is a wave function. And a wave function has two properties, which are amplitude and phase. And in this experiment, we want to look at the phase property of the wave function, and you'll see in a second why. And in order to look at the phase, we need to use interferometers, okay? And interferometers, right, basically they take two waves and they interfere it one with another, or the same wave with itself, and this is how we see the phase phenomena. And maybe the smallest interferometer, right, is simply an atom, the Bohr model of the atom. So you can think about the wave function of the electron, which is interfering with itself. If it's constructive, we have a level. If it's destructive, we don't have a level. But this is, of course, an interferometer which is harder for us to work with. Maybe it's good because then we would probably destroy it. But other interferometers that we are using is, for example, the Mach-Zehnder. So a Mach-Zehnder is an optical interferometer, which is made out of two beam splitters and two mirrors. So how does it work? So you can imagine a photon which comes to the first beam splitter. It's reflected back, then reflected from the mirror, and then transmitted from the other beam splitter. So this is one path. Another path can be transmitted from the second beam splitter and then reflected from the first beam splitter, from the second beam splitter. So basically there are two paths for the photon to come to this direction, to this detector or to this detector, and the optical length difference between these two trajectories will dictate if the photon will come here or will come here. So a Mach-Zehnder is basically a two-path interferometer. There is another kind of interferometer, which is Fabry-Perot. It's a multiple path interferometer, so it's very similar. Again, two beam splitter, two mirrors, and now the photon comes and can be reflected from the beam splitter, or it can make one round trip and then be transmitted, or it can make two round trips and then be transmitted. So there is basically an infinite series of reflection and transmission, and you need to sum them, and this again oscillates as a function of the length of the constructive or destructive interference between all of these trajectories. So these two interferometers are basically optical based, right? But if we want to make interferometers which are electron based, then we need to create a beam of electron, not a beam of light. And this is where basically quantum Hall effect comes in. In quantum Hall effect, electrons are propagating right with these 1D edges. These are the beams of the electrons. So if you don't know this, I'm really like quickly going to say that, you know, you have an electron in some vacuum or inside a two-dimensional electron gas. It moves with some velocity. It has a charge of -e. And when you apply magnetic field, basically the trajectory of the electron is bended. Okay, this is due to Lorentz force. And if the magnetic field is strong enough, this electron is actually circling around itself. So it's kind of localized at the bulk. And if this electron is at the boundary, then we have this skipping orbit picture that we all know, right? And this is the semi-classical picture of the quantum Hall effect. If you want to see the quantum analog picture, we need to think of this electron as a wave. It has a wave function, and then it can constructive or destructive interfering with itself. So it's like an atom. There are levels, and these levels are called Landau levels. And the skipping orbit itself, right? The analog is of course the 1D chiral edges of the quantum Hall effect. And we use these edges in order to create this Mach-Zehnder and the Fabry-Perot. So what you see here are basically the schemes now for the Mach-Zehnder and the Fabry-Perot, which are in the quantum Hall effect, in the electron base. So instead of a beam splitter, now you have these two QPCs. Okay, QPCs is a quantum point contact. It's like the analog of a beam splitter. So let's see how a Mach-Zehnder works. For example, you have an electron which comes to the beam splitter. It can be reflected one time or reflected second time and come to this detector. Or it can be transmitted one time and transmitted again, and then again it gets to the detector. So again, you have two paths to come to this detector, and the same idea with the Fabry-Perot, right? It can be reflected, or it can have a round trip and be reflected, etc. So these are the two main interferometers. There are others, maybe, you know, toward the end I can talk about another one that I think is very exciting. But actually the main reason to go to quantum Hall effect is not to have these edges, but actually to look at different kinds of particles. So actually the main reason to go to quantum Hall effect is to look at exchange statistics of new quasi-particles. So what is exchange statistics? Exchange statistics is basically what happens to the many-body wave function when we take two identical particles and we interchange them, okay? So in the 3D universe, we all know we have bosons and fermions, and really the fundamental difference between them is that the many-body wave function for bosons, if we take two bosons in R1 and R2 and we interchange them, we get a plus sign. For fermion, we get a negative sign. And this plus sign and negative sign, of course, is very important, has very important implications. And for example, for boson, we get Bose-Einstein condensation, we get stimulated emission, which Bose-Einstein condensation, for example, gives us superconductivity. For fermions, we get Pauli exclusion principle, we get the notion of a Fermi sea, and we get insulator, metal, semiconductor out of this difference. So exchange statistics of bosons and fermions, of course, it has a deep implication. So these are the two scenarios in the 3D universe of a point-like particles. Now in 2D universe, we can actually have a full spectrum of other kind of particles between bosons and fermions, and these are called anions. And one of the families of anions which people predict to have is abelian anion. Abelian anions is when you change to abelian anion, you get a phase of e to the I theta. So you can think about fermion as having theta of pi and bosons having theta of 0, right? So this is this minus and plus. And basically when you interchange them, you get this e to the I theta. I'm just making sure, like, you can hear me, right? It's
yeah.
Okay, thanks. Okay, now where can we see this abelian anion? So one place to see them is in the fractional quantum Hall effect, okay? Now, really 30 seconds about the fractional quantum Hall effect. So this is the description that we said before of an electron under high magnetic field. You can think about it like an atom, and it should have different levels, and these are the levels that I mentioned before, the Landau levels, E1 and E2. Now these atom, right, these localized states can actually be placed at different places in this two-dimensional electron gas, and this is actually creates a huge degeneracy. So you can think about that these E1 and E2 are actually highly degenerate, okay? And because there is a disorder in this two-dimensional electron gas, there is actually a broadening of E1 and E2. So these are called the extended state and localized states, but in the end we can just think about it that the first orbital or the first Landau levels and the second one is just broaden. Now, when we say we are in integer quantum Hall effect, right, we mean, we fill all the electrons of the first orbital, or we fill all the electrons of the first orbital and the second orbital. Fractional quantum Hall effect means that we fill a fraction of the orbital. So for example, for a filling of 1/3, we fill 1/3 of the first orbital, right? And then actually something very interesting happens. So due to electron-electron interaction, there is a gap which opens. So this is a many-body gap which opens, and the quasi-particles below and above this gap are supposed to be these abelian anions. And the edge states of the 1/3 filling in the fractional quantum Hall effect is exactly made out of these abelian anions, predicted abelian anions, which should be here. And the main idea is that by taking these two abelian anions, you can actually, and interchange them, you can get this phase of pi/3. And by the way, if you didn't see, there was like last month, there was a very interesting paper in Nature Physics, which talked about exactly this measurement of pi/3 or 2pi/3 actually in Nature Physics. So if you missed it, it's a really good work. So that's one species of anions. Another species of anion you can find in the 5-half filling. So 5-half filling, again, it means you fill the first orbital, second orbital, and then you fill half of the third orbital. And then these anions are expected to be non-abelian anions. So this is specifically in gallium arsenide. In graphene, it's a bit different. So non-abelian anion, they realize when your ground state is degenerate, and you can think about the many-body wave function as having some vector in some high-dimensional Hilbert space. And when you interchange these two non-abelian anion, you basically move between one vector to another vector in this Hilbert space, okay? So if you want to make this kind of a rotation in a Hilbert space, you basically need to multiply by a unitary matrix. So non-abelian, and that's the reason for this name, non-abelian anion, because this multiplication of matrices is non-abelian. So this, a non-abelian anion is a kind of a generalization of abelian anions. Now, this is, of course, interesting by itself on a fundamental physics perspective, but you can also use it. There are proposed theoretical schemes of how you can create a topological qubit out of these non-abelian anions. And this is important because in quantum computation, one of the major roadblocks these days is quantum error correction, and it's because the qubit itself is sensitive to noise. And a topological qubit is immune to local perturbation, and this is perhaps one of the direction that this field can go to. And this is a part of a bigger field which is called topological quantum computation. And if you have questions, I'm sending you to Netanel. He can explain you more. And also, I saw actually in 2 weeks from now there is a talk in this seminar there is a talk by Stephen Simon. So I think I'll stop here, and you can hear more about it in his talk. Okay, so what previous work was done in the quantum Hall interferometry? Okay, so this field was basically research for the last 20 years, right? And extensive work was done in gallium arsenide. I think the first work was done in Weizmann by Moti. It was a realization of a Mach-Zehnder, and then people made a Fabry-Perot and two coupled Mach-Zehnder and other Fabry-Perots, and this work is work of 20 years, but what I want to do now is basically summarize 20 years of work in 2 sentences, which I can get burned for it, but I think it makes a claim here. So
Yuval, can I ask a question?
Yeah.
Can you explain again what's the difference between Fabry-Perot and Mach-Zehnder? How do I identify which is which?
Okay, yeah. So the main difference, so this is, for example, this is a Mach-Zehnder and this is a Fabry-Perot, but I would say, like more in a fundamental difference, the difference between Fabry-Perot and a Mach-Zehnder is a Mach-Zehnder is a 2-path interferometer. Fabry-Perot, it's a multi-path interferometer. So that's one distinction. I think in more of using Mach-Zehnder and Fabry-Perot to do this interference experiment, I think the main difference is a Fabry-Perot is actually very similar to a quantum dot. So Fabry-Perot, because of this multiple path interference, there could be potentially, and I'll talk about it, if you pinch it enough, it actually acts as a quantum dot. So that's another difference between Mach-Zehnder and Fabry-Perot. Mach-Zehnder doesn't have this problem. So I don't know if I answered your question.
Thank you.
Okay. So really to sum up this like 20 years work, so Mach-Zehnder interferometer, people saw interference in the integer quantum Hall effect around 2003. And in Fabry-Perot, people saw interference in the integer quantum Hall effect in 2009. Now, it took around a decade until 2019 to see actually interference in the fractional quantum Hall effect. This is something, very lately, only last year people saw it. And it's really a big question. Why does it take a decade to move between interference in the integer to interference in the fractional? And because usually, right, you ask an experimentalist, what do you need to do to get from an integer to a fraction? He will tell you, I need cleaner sample, higher magnetic field, lower temperature. And this wasn't the problem here. And I'll talk about what was the problem, but the problem was mainly Aharonov-Bohm versus Coulomb-dominated interference, which is basically talking about a Coulomb blockade behavior. Okay, and I'll talk about it. And in the background, there are questions of edge reconstruction and neutral modes in fractional quantum Hall effect that I'm not going to talk about, but basically this is what took a decade to see interference in the fractional regime. And this is exactly, I think, the place, yeah.
Is it important that the interference was observed in Fabry-Perot and not in Mach-Zehnder? Is it going to be important in what, in the discussion?
So people saw fractional quantum Hall effect only in a Fabry-Perot, and I'll also talk about Fabry-Perot. I think the main reason that people are pursuing Fabry-Perot and not Mach-Zehnder, because at least the theoretical prediction for looking at exchange statistics in Fabry-Perot are much more, intuitive than what happens in a Mach-Zehnder. In a Mach-Zehnder, there is no, it's not clear exactly how this braiding happens. Because basically you can think about it, actually in a Mach-Zehnder, you don't encircle the other particle, okay? I can go to the Mach-Zehnder scheme, but basically a Fabry-Perot is a more understandable approach in this exchange statistic. It's basically because in a Mach-Zehnder you have a contact inside the Mach-Zehnder, okay? So it's kind of, you need to drain the quasi-particle from the center of the Mach-Zehnder. Okay, but yeah.
I have a question. Interference in waves is a single particle effect, right? And you are looking for two particle interference. So why do we use the same language even? You're causing the wave to interfere with itself. That means a single particle splits into two directions and then interferes. But what you want is to take two particles and rotate one around the other. So why do you have the same device?
Yeah, okay, so I'll get to it in a few minutes, but the idea is that you encircle, so when you do exchange statistics, right, you want to change this one particle with the other. Now you can think about it, if I just encircle one particle around the other, then I get double the phase. So you can think about the interference as one particle which is encircling another particle. So if somehow I can create a quasi-particle in the middle of the Fabry-Perot, by doing this interference of the Fabry-Perot, I encircle one particle around the other one. You see what I mean?
So you need to take this one particle in and out to see the difference or something like that, right?
Yes, no. Yeah, that's true. You need to be able to control the number of quasi-particle inside the bulk. That's important.
Okay.
Okay.
Thanks.
Okay, so this problem of Aharonov-Bohm versus Coulomb dominated, as I'll show you, is actually a very natural place to implement these van der Waals materials, and this is exactly why we started this direction. And also, all the work before was done in gallium arsenide. Quantum Hall effect interference was not seen in graphene, and when you look on something in a new system, maybe you'll also see a new phenomena. Okay, so this is the heterostructure that we use. So it's made out of graphite on top of an HBN, on top of graphene, on top of HBN, on top of graphite, on top of a silicon oxide. So a graphite is basically, so maybe I'll start from the graphene. The graphene is a conductive material. This is basically our two-dimensional electron gas. The HBN are insulator, it's just dielectric materials, and the graphite are again metallic, which we basically use as gates. Now this heterostructure is basically, it looks simple, but actually there are only like 4 or 5 groups in the world that can do this kind of heterostructure these days, and the mobility that you get here is more than 1 million, and it's possible to see odd denominator fraction, even denominator fraction, and it's really a good way to probe this kind of physics. Now, as I said, van der Waals is a good approach to answer this question, because these graphite gates can basically reduce the Coulomb interaction, which is causing this Coulomb-dominated effect, and I'll get to it later. And you can also make this HBN very thin, which will increase the capacitance to the Fabry-Perot. And I'll talk about it later, but it will increase the capacitance, and hopefully we can see a Aharonov-Bohm effect easily. Another thing is that there are very large energy gaps in graphene compared to other materials, and this is something which can help us to do this kind of physics. And also the growth and fabrication is considerably easy compared to semiconductor approach. Okay, so it's all nice, but right, what is the difficulty? Why didn't people do it by now? And actually the main difficulty is just creating a quantum point contact or creating this beam splitter. So the way usually you create a quantum point contact in semiconductor, for example, you have these 4 gates, okay? And you put different voltages on each of these gates, and by this you control the number of electrons under each gate. So for example, to create a quantum point contact, you want to have a lot of electrons under 1 and 2, and you want to deplete all the electrons around 3 and 4. And then you basically have a point contact between these 2 reservoirs of electrons. Now in semiconductor, you put the Fermi level in 3 and 4 in the gap of the semiconductor. But the problem with graphene, right? So this is the band structure of graphene, and this is the Dirac point. The problem is that if you change the voltage on this electrode on 4, you move between electrons, you move to holes, you move to Dirac point, but you don't have a gap. So how are you going to make this quantum point contact? So graphene doesn't have a gap, and this is what stopped people from making this quantum point contact. And the idea that we had is basically using the Landau level gaps in order to create this QPC. So this is exactly the Landau level from before. They are just drawn on the band structure of graphene. And what we do, we just put the Fermi level in the gaps of this Landau level spectrum. So it's basically, it's a QPC in the quantum Hall effect. It's not a QPC in zero magnetic field. And here I'm going a little bit into details. It's not so important, but the idea is that the Landau level in graphene is actually 4-fold degenerate. But if you apply a large enough magnetic field, you actually split the value and split the spins, and then you can put, you can put it at filling factor 0, or put it at filling factor 1, or at filling factor 2, and then you can create this QPC. Now, something which is interesting, so actually filling factor 0 is theoretically predicted to have these helical states instead of being an insulator. So that actually could have been much interesting, but in the end, when people measured, they saw that the ground state is different. It's some other ground state, canted antiferromagnet, which means it's actually filling factor 0 is just an insulator. And in filling factor 1, we have this one edge state which is propagating on the boundary of the sample. And in filling factor 2, again, we have 2 edges. So the way that we are making this QPC is basically we are putting here filling factor 1. So you can imagine, an edge which is propagating along the boundary. And here we put filling factor 0. So basically when the edge reaches here, it starts to climb, right? Because it cannot come into filling factor 0. And then at this point, it can either tunnel to the other side or can be reflected, okay? So of course, I'm pointing at the gates, but actually the physics happen under in the 2-dimensional electron gas. So this is the way to make this QPC. Okay, so how do we make these devices? So this is a picture that I like just because it shows you, what you start with. So these are the initial flakes that we start. This is like a graphite flake and a BN flake and graphene flake. And this is, in the end, what's changing the MBE. And you take this glass slide and you take PDMS PC stamp, which is basically a polymer, and you pick up the upper graphite, and then you pick up the top BN and the graphene and the bottom BN, and then you land it on the bottom graphite. And then in the end, what you get this stack, okay, this sandwich of different flakes. And you can engineer, you can do here whatever you want. And I'll talk about toward the end, I'll talk about more maybe exotic things that we are doing. And we get this sandwich, and then we need to fabricate it. So we have this stack, we do top gate etch, stack etch, normal contact. We do some air bridges because we need to contact the upper graphites. And then we do this etching in the upper graphite, which is basically dividing the upper graphite to 4 different gates, okay? So I showed you these 2 slides in 15 seconds, but this is actually, the 2 years of this work. Okay, so this is the QPC device. So here you can see, this is the top gate. It's divided into 4 regions, and each of them is contacted by these air bridges. And these are the normal contacts, okay? Okay, so this is a kind of a scheme, a measurement scheme of the QPC. So to have some common language, so this is we can call it the filling in the bulk, nu B. This is the filling right under the split gate. And this is the filling in the QPC itself. Now, this filling in the QPC itself, I don't mean that, you know, there is actually a quantum Hall region there. It's more telling you like how many edges are transmitted or reflected. Okay, and you'll see as I'll show you in a second. Now, the measurement that we do is quite simple. Like we source current from this contact, so you can imagine an electron which comes, right? It comes to the QPC, and then it can either be transmitted or it can be reflected. And what we measure VT. We measure the chemical potential between these two contacts, which is basically asking the question how many electrons stayed at this edge as opposed to how many electrons tunneled to the other side. Okay, so just to have like some thought experiment. So if all the electrons are just continuing, all the edges just transmitted, then the chemical potential between these two contacts is 0. If all the edge is reflected, then this VT is some finite value. It's R quantum times the current that you source. So this is basically the way that you can characterize this QPC and see that it's working. And the measurement were done in 50 millikelvin and most of them around 8 Tesla. Okay, so what I'll show you now, I'll show you like one of the measurements. So what here, the filling in the bulk is filling factor 2. Okay, so it's filling factor 2 here and filling factor 2 here. So we have here 2 edges. And under the split gate, it's filling factor 0. Okay, and what we are changing this new QPC. We are changing the position of the saddle point. Okay, so we start by just having 2 edges which are reflected back because new QPC is 0. And then you see that VT basically has some finite value. It's RQ divided by 2, 20, like 12.8 kilo. And then when we open the QPC a bit, right, we have the beam splitter for the outer edge. So this is this drop in VT, which is, this is exactly the operation of the beam splitter, right, on the outer edge. And then there is a region that one edge is fully transmitted, one edge is fully reflected. This is this plateau. And then you have the beam splitter of the inner edge. Okay, so this is this drop. Okay, and then both edges are just transmitted, and then VT is 0, as we said before. So basically, these 2 regions, this one and this one, are showing you the beam splitter operation, right? The QPC operation on the outer edge and the inner edge. And this is something that, you know, people try to make. So for us, it was really encouraging seeing this result. You can also measure VR, and you can see that it's complementary to VT, right? One thing which you immediately you notice that the level here and the level here of VT and VR are not the same, and this is because this measurement is actually not exactly a 4-probe measurement, and we are sensitive to the ground resistance. So there is some asymmetry in the ground resistance between this contact, and this is why it's not at the same level. But nevertheless, the QPC works at filling factor 2, and we can create these beam splitters. Okay, so this is QPC, which is operating at filling factor 2. We can also make a QPC, which is working in filling factor 1. So you see here you have one step which is coming down and one step which is coming up. You can also make the same in filling factor 6. And then you basically, you see 6 steps, 6 edges, and you can see them both in VT and VR. And here you can see this is, it's not so important, but the main idea is that the phase space of the QPC is actually more complicated, and you can make other realization with this QPC. But you know, the lower panels are what's important. What is important is that actually you can put this QPC in a fractional filling. So you can put the bulk in 3 + 1/3. Okay, so this means you have 3 integer edges here and 1 fractional edge. And then using this QPC, you can actually you can operate the beam splitter on a fractional edge or an integer edge. Okay, so you put again filling factor 0 here, and you tune the saddle point of the QPC, and this is what you see here. So what you see here is an operation of the QPC. So here the beam splitter is on an integer edge, and here the beam splitter is on a fractional edge. And you can also see it by the sizes of the step. This step is 1/3 of the integer edge. Okay, so
how do you
we have
see exactly what is the size of the integer step? I mean, in fact, you know, all these edge states are mixed. It's hard for me to. I'm not sure there's a good definition for. It's not these edge states stacked in a very ordered fashion or anything.
So what this measurement, for example, what this tells me is that the 3 integer edge and the fractional edge are completely separated, like spatially in space, because you know, as you pinch the QPC, you see 3 steps. I didn't show it, but there is actually another 2 steps above, and then there is the inner integer edge and then a fractional edge. So you know, these 4 edges, these like 3 integer edges and 1 fractional edge is completely separated from one another.
Showing here is 1 integer step. This.
Yes, exactly. There is another integer edge here and another one here. I just wanted to concentrate here on the fractional edge.
And what's the difference between the blue and the red?
So the blue and the red are basically, so in these devices, I actually had 2 QPCs, okay? And the red one is the left one and the blue one is the right one. So it's just repeating the same measurement in different QPC. It's basically a Fabry-Perot device that we'll see in a second.
Other integer steps are exactly of the same size. I mean, I'm just wondering.
Yes. The only difference actually between the integer edges is this grounding resistance, which is a bit changing because it depends if the edge goes, if it's transmitted or reflected, but it's something we can calibrate. I would say like up to now, there is nothing, you know, surprising. It's just showing you that you realized a beam splitter in the fractional and the integer regime.
This last step is between 0 and 1/3 or between 3 and 3/3. So this is.
So it's between 3 plus 1/3 to 3. Because
when you say 0 on the y-axis, what does it mean? I mean, I thought.
Yeah. I'll explain it. So if the filling of the new QPC is 10/3, which means 3 plus 1/3, all the edges are just continuing, right? If all the edges are just continuing, a measurement of VT is like a measurement of RXX, right? So that's why you see here 0, because all the edges are just continuing. Now, if 1/3 is coming back, then I should see 0.8 kilo. I can do this calculation, but that's the reason you see this 800 ohm.
So you mean
what's special about 800 ohms?
Yeah, 800 ohm is just, you know, you need. So what's the resistance of this 3 plus 1/3? Okay, if you do a 2-terminal resistance, it's just 25 kilo ohm divided by 3 plus 1/3, right? And then you need to calculate what is the resistance which is divided to the 1/3. So this resistance that divided to the 1/3 is 800 ohm. So that's basically. I answered your question, Asa. I'm not sure if.
Well, it would be simple if you just showed the 0 to 1/3 first, because you see the Laughlin state, the 0 to 1/3, you see 1/3 coming back?
Yes. I actually show you. Here I show like a bulk conduction of 3 plus 1/3 instead of 1/3. So it might be, you know, maybe not the best pedagogical but it's the same idea. This 1/3 fractional edge that you see, it's also a Laughlin state.
Okay, that state has been measured. I don't know. That's in the bulk. I mean, people saw this
Yes.
filling factor 3 + 1/3 is a plateau that people see.
Yes. Yes.
Okay. Okay. I didn't know that.
Okay. So basically, what I showed you up to now. By the way, Netanel, how much like accurate in time I should be?
Not very accurate, you know.
Okay, so
Not as accurate as the quantization in the quantum Hall effect.
Okay, when I see people starting to fall asleep, I'll stop. Okay, so it will take probably 5 more minutes than what I needed. Okay, so this is the QPC. So now we can basically go and look at a Fabry-Perot. Okay, we can just take 2 QPCs and we can build a Fabry-Perot. So this is the same image that I showed you before. So what you can see here, it's very similar to the QPC that I showed you before, only now there are basically more gates and more bridges, you know, to contact each gate, but it's very similar. So now you can think about this electron which comes from here, right? It's advancing to the first QPC. If you put here filling factor 0, 0, and 1, 1, it reaches the first QPC. And then here you have the second QPC, so you tune it to be exactly where you want. And then you can realize this Fabry-Perot, okay? So what you need to imagine here, right, is you have an electron which comes, or a quasi-particle, it can come like this and be transmitted, right? Or it can come and can make a round trip and then be transmitted, right? Or 2 round trips. So this is what creates this Fabry-Perot. And of course, this electron is charged, so it's coupled to the Aharonov-Bohm phase by the flux which is penetrating this area, and this is what dictates this interference pattern that we should see in a Fabry-Perot. And you can repeat this experiment, right? You can, instead of 0, 0, 1, 1, you can do 0, 0, 3, 3, and you can interfere the outer edge or the inner edge or whatever edge you want, and different edges show different behavior, and I'll talk about it. But really, you know, the essence of the device is just this interference, right? This is the essence of the Fabry-Perot, and you have this electron which continues, or it makes a round trip and continues, and you can calculate what is the transmission of this multiple path. And R1 and T1 are the parameters of the left QPC, and R2 and T2 are the parameters of the right QPC. And this theta is basically the Aharonov-Bohm phase. Okay, so the Aharonov-Bohm phase is simply the area times the magnetic field. It's the flux divided by phi naught times the charge of the quasi-particle divided by the electron charge. So this is basically the Aharonov-Bohm phase. And where is the exchange statistics comes in? So if I can control and I can put a single particle inside, a single abelian anion inside, then basically you can imagine it as having this exchange statistic twice, right? And this will introduce this, this will introduce this exchange statistics, okay, exchange statistic phase. And this is exactly what you want to look at, okay? That's the experiment of this is how Fabry-Perot interference like connects to exchange statistics. Okay, but right, in this experiment, I'm mainly talking about the integer quantum Hall effect interference, and I want to show you what is this main problem that took a decade to overcome, this Aharonov-Bohm versus Coulomb dominated interference. So this Aharonov-Bohm phase, right, it's A times B. So if we want to stay at the same interference as we increase magnetic field, we need to decrease the area, right, to stay at the same phase. So if we look at the interference, okay, this is just the interference. You can think about it like the current which is draining here. This is the interference as a function of magnetic field, the x-axis, and the area on the y-axis. So right, so this is the prediction. This is a theoretical paper. So as you increase the magnetic field to stay at the same phase, you need to decrease the area. And this is exactly what people did. So in 2009, Charlie Marcus, he was actually in the same lab as I'm in now, because Philip Kipp changed Charlie Marcus in its flow. So we are continuing the same interference experiment in the same flow. But basically what he did, he measured a 20 micrometer square Fabry-Perot. So this area is around 3 micron square, but he made a Fabry-Perot in 20 micron square, and what he saw is exactly what's predicted. So as the magnetic field is increasing, the area is decreasing. Now, what you actually want to do, you want to make these experiments in relatively small Fabry-Perot, not in big Fabry-Perots, because the coherence length of the fractional edges is actually expected to be low. That's what we see experimentally. So you want to make Fabry-Perot as small as possible. Now, when you make it, so this is another paper a year after, so I'll just rotate it that the x-axis will be magnetic field and the y-axis will be the area. So what you can see here that there is no B dependent to the oscillation. So this is a Fabry-Perot which has an area of about 3 micrometers square or 4 micrometers square. And you can see that they see interference as a function of area, okay, the y-axis, but they don't see interference as a function of magnetic field, okay? And this is basically, there is a lot of theory about it, and this is actually written in this paper that I cite, but it's mainly because the area is actually changing as a function of magnetic field. And what happened is when you increase the magnetic field, actually the area shrinks. So there is a kind of a breathing of the area as a function of magnetic field. And this is why actually this formula is not correct for this regime of Coulomb dominated. So on the right, you can see this is basically the Coulomb dominated regime. And on the left, you can see what people call the Aharonov-Bohm dominated regime. And it's actually even more complicated. So what I showed you before was an interference of the outer edge. If you look at the interference of the inner edge, then it's actually even opposite. You see, you stay at the same phase, but when you increase magnetic field, you also increase the area, okay? So this is basically the main, this was the main roadblock for this line of research of seeing fractional quantum Hall effect interference. And this is exactly what I mentioned before, where I think like van der Waals can come in and contribute. And there are, of course, other experiments that we can do, but this is something which is very, can be solved elegant by van der Waals heterostructures. Okay, so this is the scheme of the Fabry-Perot. So what you can see here is a kind of a scheme of an interference of the inner edge, okay? So the bottom BN, we make it around 20 nanometer. The upper one is around 50 nanometer. And it's actually important in terms of the fabrication that we do. And for an area of an interferometer, which is around 3 micrometer square, we get a charging energy, which is around 8 microelectron volt, which is comparable to temperature. And this is the regime that we want to see in order to be able to see a Aharonov-Bohm oscillation. Another thing is that you see this scheme of Fabry-Perot is gate defined. It's not H defined. And this is actually something that I'll talk about toward the end, but it's actually extremely important to make this interferometer gate defined and not etched. Okay, so this is again the QPC that I showed before. So these are again the two QPCs. So the blue one is the left QPC. So the blue one is this left QPC and the red one is the right QPC. And this is the beam splitter of the outer edge and the beam splitter of the inner edge. What I showed you before, I'm just reminding. And then what we do, we basically park our reflection coefficient here. So the right QPC is around 0.5 reflection and the left one is at 0.1. And then what we can do, we can change the plunger gate. When we change the plunger gate, we basically change the area of the interference. And what we see is this interference. So this for us, we were really happy to see this interference. So this is the interference as a function of plunger gate when you measure VT. And you can also measure VR, and you can see that it's exactly 180 degrees to this VT, which is not surprising, but that's the measurement. And as you sum both of them up, you get a straight line, which is basically telling you that there is no bulk conduction. It's a sanity check, okay? Now,
how do you know that this by changing this gate, you're not changing the transmission? I mean, it looks very unstable, the value of the transmission. There's lots of oscillations in the point of parking it.
here.
So how do you know that, changing some other parameter doesn't,
Yeah. No.
connection?
Yeah, you mean like a cross capacitance measurement, right? Like some kind. Yeah. So I know because first of all you'll see in a second, right, that as a function of magnetic field, let's say a magnetic field measurement. If I would show you oscillation as a function of magnetic field, you won't ask this question, right? So I can't hear you. You are muted. But,
I would maybe, it would. I mean, they could still ask this question, but maybe, it would be less.
I think that.
But the thing is that, you see that the transmission or this reflection coefficient is very unstable at the point you're parking it. So,
yeah.
Right.
This is because there is some inner structure to the QPC, but
yeah.
You won't get these like 30% oscillation, right? If from these kind of you see what you are saying is basically, maybe you're just traveling on this red QPC,
yeah.
But this won't give you this oscillation, right? 30% oscillation. So okay. By the way, another thing that I can tell you is, for example, if it comes from that, let's open one QPC, change the plunger gate, and see how it acts. And if you do that, you see that it's completely flat. So it's
okay. That's okay.
More convincing.
Yeah.
Okay. So, okay. There was another question. Okay. So this is as a function of the plunger gate, and you can look at the visibilities. The visibility that you see here is 12%. We also saw around 30% visibility. I'll show it later. And from this, you can do, of course, you can do an FFT. You can extract what's the periodicity, and you can extract from it the capacitance between the plunger gate and the edge, which can tell you about the electrostatic which happens here. But maybe the more interesting question, right, is do you have Aharonov-Bohm or Coulomb-dominated regime, right? So we see what I mean. Like here we see as a function of area oscillation. The question if we see as a function of magnetic field. So this is the measurement, right? And you see that similar to what I showed you before, when you increase magnetic field, you need to decrease the area. So this is exactly following this A times B relation, and this is the Aharonov-Bohm interference. So this shows that in this device, we are able to see this Aharonov-Bohm interference. Now,
what got rid of the Coulomb effect in your device?
So can you ask again?
What got rid of the Coulomb interaction effects that you have in gallium arsenide?
Okay, so two main things. The first one is that the bottom HBN is very thin. So this made the capacitance of the Fabry-Perot to the world much larger, which reduced the charging energy. So that's the main reason. Another reason is also that actually the dielectric constant of the HBN is 4, and in gallium arsenide it's 13. And this is actually important because there is also capacitance which is important between the edge and the bulk, and we are reducing this capacitance. So it's actually 1 + 1 in that respect. But the main contribution, I think, is the reduction of the charging energy. Okay. So now what you can do, so this is the Aharonov-Bohm oscillation that I showed you before. You can make an FFT of it, and then you see that the main peak is exactly at 3 micrometers square, which is the area of the Fabry-Perot. You can also see a second peak, which basically means that the coherence length is larger than twice the size of the length of the perimeter of this Fabry-Perot. Now you can choose other working point, right? You can open the Fabry-Perot more, and then you see only this peak. You don't see the other peak because the less electrons are doing the second trajectory. You can also close the QPC more, and then you can see a third trajectory. So it tells you that the coherence length you can still see interference even around 18 micrometer. And another thing which is interesting is you can see that in all of this phase space, we see a Aharonov-Bohm oscillation, which kind of showing you the robustness of this design. Okay, so now, as I said before, you can basically, so this is the Aharonov-Bohm, and this is the 2D FFT, and you can extract from it. I didn't show it here, but if you ask, I can talk about it. We can extract the Fermi velocity of the edge and the coherence length out of these measurements, and we can do it for the inner edge, for example, in filling factor 2, and we can do it in the outer edge of filling factor 2, and you can do the same thing in filling factor 3. So in filling factor 3, you have 3 edges, and you can do the same thing for filling factor 3. So it's a lot of measurement, and I kind of tried to sum it in these 2 panels. So this is in filling factor 2. So in filling factor 2, you have the inner edge oscillation and the outer edge oscillation. And in filling factor 3, you can see that, again, you have 3 different oscillations. And something which is different than gallium arsenide, for example, in gallium arsenide, it's always the outer edge which has the highest visibility, okay? And actually in our devices, it's the middle edge. And I think this is actually connected to the fact that we do gate-defined versus edge-defined, because you can see that actually the coherence, so the upper number is coherence length and the lower number is the Fermi velocity. And you can see that as the Fermi velocity here increases, also the coherence length, okay? So it's not one-to-one, but it's kind of telling you that as the Landau level is steeper, then you get a higher velocity and higher coherence length. Okay, so this basically talks about edge mode velocity versus coherence length measurements. Another thing that, you know, it's nice that we can learn here is we can look on the coherence length of the bulk of the graphene and compare it to the coherence length of etched graphene. So how can we do it? So usually we put the plunger gate at filling factor 0, but you can actually put the plunger gate at filling factor 1 or filling factor 2, and then you should see, and then basically the edge is propagating along the etched graphene. So you can extract from it what's the coherence length of the graphene, of the etched graphene compared to the gated graphene. And what you see here, so
edge is this, Yuval? Is known, or is it just a mess? Is it like an armchair, or?
So it's a mess because it's etched. So I don't. It's like a mix between them.
Okay.
Okay. So.
Excuse me.
The x-axis here.
May I ask a question? How do you extract the coherence lengths?
Okay. So the way we extract the coherence length is you have the visibility. Okay. You can calculate the visibility as a function of the, let's say it's like this. So if the coherence length was infinite, then the formula that I showed before, right, you remember this T1 and R1, that was for an infinite coherence length. You can make the same formula for a finite coherence length. And it's basically telling you that, you know, trajectories which are widening twice or 1/3 should have a lower contribution. It's like weighting the different trajectories according to the coherence length. And then what we do here, you basically change the reflection and transmission of these QPCs, and you compare what should be the coherence length in order to see the visibility that I'm seeing, okay?
Yes.
So that's a way that you can.
Yeah. In that formula, the dependence on the coherence length is exponential?
Yeah, yeah.
Yes?
Yes. It's
okay.
You know, L divided by the coherence length.
No, this I know, but it enters into an exponential attenuation, or not?
Again, say it again.
In the formula that you gave for the infinite coherence length limit, when you put a finite coherence length, how does it appear? It's an exponential dependence on L divided by L phi, or it is something else?
So when you introduce the coherence length, it's an exponential decay. But when you calculate the geometric series, then it's not a dependence in an exponent. I don't have the formula here, but it's not like a difficult calculation.
Mm-hmm. Okay.
But you're extracting this L phi based on kind of 3 data points, is that right? Or
no, it's not that. It's not 3. It's actually 600 data points, because every reflection and transmission that you put for the QPC is basically helping you to find this coherence length.
I see. But in terms of length, you only have 3 options or something. Is that right?
In terms of length, you have 3 options. Yeah, but you are actually like using the other degrees of freedom of R1 and T1 to find instead of the length.
Okay.
Okay, so the idea here was basically to find the coherence length of the gate defined versus the edge defined. And what you can see here, you can see that as we change the plunger gate, okay, from filling factor 0 to filling factor 2, so in filling factor 0, we see very large oscillation, and as the edge is on the physical edge, then we lose completely the visibility. You see that the visibility is very low. So this tells us that the coherence length is probably very small in the physical edge. And you can think about it like when you move, so right, the edges simply move to the physical edge of graphene, and this physical edge is creating some decoherence processes. Now, the way to really be sure that this is what's happening, so what you can do, you can stand at each of these plunger gate values, and you can scan magnetic field, okay? And then you can do the FFT of this magnetic field. So maybe it's a bit complicated slide, but the main idea is in this lower panel, and this lower panel basically shows you the coherence length of the gate defined versus the coherence length of the edge defined, okay? And it shows you that the gate defined is an order of magnitude higher in coherence length relative to the edge defined. So we are still able to see interference in the edge defined, but the coherence length is much, much longer, okay? And this is actually important because, in the end, you want to make schemes for Fabry-Perot, and this teaches us that we have to use gate-defined Fabry-Perots. Okay, so the conclusion, okay, so I showed you, I demonstrated a tunable QPC in the integer and the fractional quantum Hall effect. We saw AB-dominated interference in the integer quantum Hall effect in small Fabry-Perot, measured edge mode width, velocity, and coherence length, and compared gate versus edge coherence length. So 3 slides about next steps and basically what we are doing now. So what you saw now is right, it's a picture of around half a year ago. So now we are looking at these exotic states, and we are trying to see this Fabry-Perot oscillation in the fractional quantum Hall effect. And the main thing that we are trying to do is we are trying to reduce the size of the Fabry-Perot and improve the electron temperature and go to higher magnetic field. So it's we are really trying to improve our dilution system and filter the noise and reduce electron temperature. The electron temperature that I showed you is around 50 millikelvin. It's actually quite high for this kind of measurement. But what I want to say is actually that what I talked about until now was basically creating a heterostructure that you can use in order to see interference in the fractional quantum Hall effect. But actually the van der Waals materials are actually a much richer, they have much richer physics than what I showed you. So of course, this is the obvious direction to go, but we are actually trying other directions. And one of the direction is actually when you put in-plane magnetic field, or you put all of this stack on top of, instead of silicon oxide, you put it on top of an STO. So I said in the beginning, in filling factor 0, it should have been helical states, but actually people saw that it's an insulator. So what we are trying actually to do now is to recreate these filling factor 0 helical states and to create interferometers which are actually interferometer in the spin quantum Hall effect. So this is what I'm trying to do now, and also I think what I intend, to do in the future also. So by making this quantum spin Hall effect interferometer, so this is called the Sagnac interferometer. People in optics know it more than like quantum transport experimentalists, because usually we don't have these helical states in our systems. But what's interesting is that if you couple it to superconductors, you can actually get very interesting physics and very interesting new physics, which is talking about artificial 2D topological insulator and topological superconductor interference. And I think this is a field which is really hard to access, because there are not, of course, there are not a lot of materials which has a large coherence length, like graphene. Mercury telluride, I think, is the only one which is a good candidate. And I think even until now, nobody made a QPC in mercury telluride, really in the quantum spin Hall effect. Another direction that we are trying, so instead of graphene, you can actually put twisted graphene. And this is very interesting, because now you can make a QPC. So you can imagine two superconductors, right, that are touching in this point between these two, like a point contact between two superconductors. And you can also ask questions about Chern insulator physics. And of course, you can put other materials of van der Waals if you think about a good and interesting experiment. So I'm just leaving with this picture, which I think it's kind of nice, and thank you.
So thank you very much, Yuval. So any questions?
Do you have any data on 5/2?
Okay, so if I had, I would start the presentation for it. But so in graphene, it's actually instead of 5/2, it should be half. But I think maybe before going to the non-abelian, right, you should see the abelian fraction. So because it's supposed to be easier, the gaps are larger. So this is what we're trying to do now. So the answer is regrettably no.
Can you explain?
No, go ahead, Jesse.
You said van der Waals material. I didn't know what's van der Waals and why should van der Waals be special?
Okay, so van der Waals materials. Okay, maybe I should have done like a better introduction. But van der Waals materials are basically layers of 2D crystals, right? So graphene, for example, is a 2D material, and its crystal there is a covalent bond in the in plane, and there is a van der Waals bond to another layer. So for example, a graphite layer are many graphene layers, one stacked on top of the other. And you can ask, for example, what's the, what is special on van der Waals layer compared to other? So one of the immediate things that I can say, so in the fractional quantum Hall effect, for example, you can do one monolayer of an HBN. This is something which is not possible in semiconductors, in MBE, okay? But in van der Waals, you can do it right in like relatively fast. So by the way, there are incredible, advantages of using gallium arsenide, and there are advantages of using van der Waals. It just depends like what physics you want to look at. Another thing is, instead of graphene, you can use another material. You can use twisted graphene. So I would say, like, to answer this question, I think just the physics that you can access with van der Waals has a much larger variety than the one that you are accessing with gallium arsenide, for example. So there are very important questions that you can continue to ask with gallium arsenide, but we want to do new stuff. So
thank you.
I have a question.
Yeah, I didn't hear you, Amit.
So I can't towards the end, there was a little bit too many details. You started by saying that you are looking for anions or non-abelian statistics. Do you plan to have found anion?
No. So no, maybe, you know, it's a, do you see, I'll just rephrase for a second, like, do you see an evidence for abelian exchange statistics? So the answer to this is no. For this, I should show you interference in the fractional quantum Hall effect, and I should show you braiding. I should show you phase jumps in the abelian case, or in the non-abelian case, it's a bit more complicated. So I didn't show it yet. Nevertheless, I think it was a good advancement in my, like, just I'm saying it because, you know, when we started this direction, people didn't know how to make QPC in quantum Hall effect. So you need to compare, you know, 20 years of gallium arsenide compared to graphene. But, you know, we are headed there.
Thank you.
Yuval, did you try to measure the dependence of the coherence length on all kinds of parameters like temperature?
Yeah, so I actually, I'm not sure I have it here. Yeah. So this is, for example, the coherence length as a function of temperature. So you basically see a decay as a function of temperature, and we can attribute it to actually to there is a lobe structure in the Fabry-Perot that we can see, and actually this temperature, what it does, it smears the lobe structure of the Fabry-Perot. From the lobe structure, we extract the edge mode velocity.
Mm-hmm.
So we measure the coherence length as a function of bias, and a function of temperature, and a function of magnetic field.
So it's mainly an issue of kind of scattering with phonons, or what?
You mean why don't I see?
Yeah, what's the main mechanism for this?
Okay. So I think it's mainly electron temperature. I think it's mainly electron temperature, and also, you know, I started working with a fridge, and I need a better filtering on this fridge, basically. So that's what I'm doing these days. I'm improving, you know, the filtering and the electron temperature to be able to go to the fractional regime. But I think, you know, I'm just like, maybe I'm repeating myself again, but I think going to fractional, it's extremely interesting. And that's, you know, that's my main goal right now. But I think one of the things which is also interesting is trying these other schemes, having interferometer in the quantum spin Hall effect, and in twisted devices.
I'm still puzzled with this phase coherence length. May I ask again? So
yes.
What I understand from this last graph that you just showed is that you extract the phase coherence length from this Fabry-Perot, those peaks, and you say that the visibility of those peaks gives you a direct information about L phi. Again, could you explain how you extract this? I don't understand.
Yeah, okay. Second. I think I have. I should have put this slide here, but the main idea is this. So when you want to calculate the transmission of a Fabry-Perot, so it's basically just an infinite series, right? Now you can imagine that instead of this infinite series, instead of this e to the I phi naught over 2, I write e to the I phi naught over 2 minus L divided by L naught, right? And then I calculate again this infinite series.
L naught is the current length, right?
Yes.
It's also called L phi. Okay.
Exactly, L phi. And then you get a new formula, and this new formula depends on T1, T2, R1, R2, L, L phi naught, and phi. And then I change T and R, okay, for a particular L, and I can find what is the L phi.
I thought that this formula, this very formula that you used, had to be modified in the case of a strong magnetic field. If you have, but apparently you say that it's still valid to.
No, yeah, I think this formula is valid. It's just an incident. You know, this Fabry-Perot in the end is very similar to an optical Fabry-Perot. It's the question is what is phi, right? If it's Aharonov-Bohm or something else.
Yes. Yes. Okay. Okay.
It's I'm not sure. I didn't get to the end of, you know, ירדתי לעומק דעתך, אבל in the end, it's just like adding here like a coherence length argument and calculating.
Because, for instance, when you measure magnetoresistance, even for weak magnetic field, for that kind of system that you want to use this transmission formula, the dependence on the phase coherence length is not exponential. It's a power law in two-dimensional systems. So it's very important that it's two-dimensional. But here what you use, perhaps it's because it's one-dimensional.
Yeah, it's one-dimensional, it's chiral, so there's no backscattering either.
No, but the fact, yeah, perhaps the fact that it is one-dimensional, but even though this is also not exponential with the phase coherence length, I think. But okay, I have to think about it. Anyway, in two dimensions, this is certainly not exponential.
In two dimension, I wouldn't do this infinite series.
Yes. Okay. Okay, I have to think about this. It's a very good, very interesting point. Okay, thank you.
And if you have actually some, you know, there I'll be more than happy to hear.
Okay, okay. If I have some remark, I will send it to you. It's very nice, very interesting. Thank you.
Can I come back to the question of Amit? So you measured interference, and
See?
for a third, but what? I'm sorry? אי אפשר לשמוע?
עכשיו שומעים.
No, sure.
I want to come back to the answer and the question of Amit and the answer you gave to him. So you did measure something about in the fractional quantum Hawking effect, you measured some interference. And what was missing to see the quasi-particles?
Okay, so I probably didn't explain myself.
You probably did, and I didn't understand.
So what I showed a QPC, which is working in the fractional regime. So this means you have a QPC, which is partitioning and working in the fractional regime. I also showed actually something else. Where is it? Okay. I didn't put it here actually in the paper. It's written, but what I want to say, the QPC we showed for fractions and integer. The interference we showed only for integer, but we actually saw the interference for bulk, which is fractional, but for one of the integer edges, but not for the fractional edge. So
thank you. That makes it clear. Thank you.
Okay, no problem.
Well, do you think that there's an option to in graphene to create, you know, like traps that traps, you know, quasi particles or quasi holes?
Yeah. So actually, one of the things that you know, first we need to see a fractional interference, but what we actually, one of the things that we have, and we have such a device that we take this, okay. So in the middle of this Fabry-Perot, we actually etch it and then you have a gate which is another gate which is in the center here near the bridge. And then basically by controlling this gate, you want to be able to control the number of quasi-particle inside the interference. So this is something, you know, I think it's completely possible, but, you know, first you want to see like the interference in fractions and then, you know, to continue in that direction.
The main obstacle you think for seeing the interference is the temperature? What's the main obstacle?
I think it's only temperature. And I have like good reason to believe it because you see, I said like it took 10 years for people to see Aharonov-Bohm interference in fractions. But actually what they saw during this time is they saw Coulomb-dominated interference. And I think the reason that we don't see Aharonov-Bohm interference is because, you know, quasi-particles, maybe I'm optimistic, but I think like quasi-particles are actually jumping in and jumping out. And this creates some kind of a phase averaging, and this is what obscures the interference. And not if I would see a Coulomb-dominated interference, I would actually be, you know, more pessimistic. So that's why, you know, I'm continuing to go in this direction.
Okay. Other questions?
Comment. מאוד נהניתי.
תודה, עמית. I like it that we finish in an optimistic note and not in a...
וגם למדתי דברים חדשים.
מגניב.
Okay. So if there's no other questions, thank you, Val.
Thank you very much. Thank you.
Thank you.
Bye.
Bye.
Thank you very much.
Bye, thank you.